Let's see if you have any questions first before we start new material.
So
Yeah,
you defined an extra term energy density of state, which is G of E.
yeah.
But you said that this e raised to minus beta e is already a probability density term for a continuous variable if energy is continuous. Then why we need to an extra term like G of E?
Oh, no, 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 no. We did not. E to the power of minus beta E is the energy density for a is the probability density for a particular quantum state with that energy E. And there could be a gazillion number of such states, which is indicated by the G of E. So the product of G of E times E power minus beta E is the probability density.
So e raised to minus beta.
Okay, let me actually clarify that. So what I meant was the following. So we haven't yet done um, quantum states, but let us say we have discrete values for the energy for a particular system. Okay, right?
Yes.
Now, uh, these are energy levels for the system, but imagine a situation where these energy levels are extremely close by, where we can actually treat them like sort of a band. You are all familiar with bands of energy levels in semiconductors, and you have at least heard of these kind of things in metals and semiconductors, right? Now, this is a discrete spectrum, and this is a continuous spectrum, more or less. Okay, that is what we usually refer to when we say discrete and continuous. Now, what did I say? The e power minus beta ei divided by sum over I e to the power of minus beta ei over all I, where I is the states of the system, the distinct states of the system. Okay, there can be many states, many I's, many states, that is I's, for which, let us say, E, E, sorry, I1 to some I capital M, such that all of these have energy E. Okay. Now, the probability density for this energy will not just be e to the power of minus beta ei, but it will be sum over. If you ask the question, what is the probability density for the system to have energy E? How will you answer that question? That would be
Then we should
rho
sum
of
over that
rho
thing.
of E dE will be summed over all I equal to 1 to m, I1 to m, im, right? E to the power of minus beta ei or E divided by the, so this is basically m times e to the power of minus beta e, right?
Yes.
Divided by the normalization factor. That is how you, so the questions are different. The question is not about what is the probability for a particular quantum state. That is what Gibbs principle arrives at. And using that, we can arrive at what is the probability that the system has a particular energy E. And you will immediately get this multiplicity factor, which is usually a function of E. And this is for discrete levels. In the continuous limit, you will essentially get this to be G of E. Let me be consistent in my notation. Here I am writing the probability itself, P of E, because I am treating this as a discrete system. In the case of a continuous system, this will become e to the power of minus beta e dE by integral of whatever, and then I have to call this rho of e dE. Is that clear?
Yes, sir.
Yeah.
So just to clarify, because when you consider n molecules of ideal gas and derive the expression, we just calculating what is the probability that a particular state in a particular energy.
No. In the ideal gas case, so this energy thing was, so I also set up the Gibbs principle for the phase space, right? The probability density that the state of a system has coordinates and momenta in a small region of phase space. This is the probability that the system is in that region of phase space, right?
Yes,
This
sir.
is an n dimension, it's a 6n dimensional space in which you are considering a 6n dimensional infinitesimal small cube of of sides dx1, dx2 like that. It's a cuboid, you can say. Okay,
Yes.
this probability from Gibbs principle, any such probability depends only on the energy of that particular state. So therefore, this will be e to the power of minus beta e, which is a function of x1 to p3n. Okay, divided and times dx1 to dp3n divided by integral. It's a multiple integral over all these variables of the same probability.
So why we are not considering the multiplicity factor in the
The multiplicity is actually inside this volume. So inside that volume, there could be several states which have the same probability. So when you do the integration over a finite volume, that multiplicity is automatically taken care of. We will
Sir,
actually look at that right now in a few minutes.
Okay, so yeah.
sir,
Yeah,
how could we have multiple states on the same coordinate with the same momentum?
we are not considering multiple states with the same coordinate and same momentum. I'm saying if you compute this probability over a small volume of phase space, there will be many states with many coordinates and many momenta, right? Because you are treating coordinates and momenta as continuous variables. So this volume will have an infinite number of such states.
Yes, sir.
And there could be many of these states which have the same energy.
Yes, sir.
That is what I mean. We will see that. If you stay with me for a few more minutes, all these things will be clarified. But the main thing that you need to understand is that if you ask the probability for a system to be in a particular state, the answer is the Gibbs principle, which says that the probability depends on the energy of that state. And if you ask the question, what is the probability that the system has a particular energy, and not asking the question, what is the probability that the system is in a particular state? These are different questions. For the former question about the energy, you will have the multiplicity factor come in. And that is what this, that is what this expression here is. Whereas this expression here, if you notice carefully, this is not in energy. Uh, it's not in the energy space, meaning energy is not the integration variable here. All right.
Yes, sir.
Yeah. Okay. So now using this Gibbs principle, we were computing the average value of the energy for an ideal gas. Okay. And we set up the expression to be integral E of x1 to p3n. That is, you write down the energy as a function of all the coordinates and momenta and multiply by the probability density and then integrate over the volume of phase space, entire volume of phase space. This is the expectation value of energy, and this same analysis can be extended to any variable. Energy is a very interesting variable for thermodynamics, so we are considering that first. But in principle, this exact same formula holds for any physical observable. Now, and we made a lot of progress last week. So let me just quickly write down the expression. So for an identical an ideal gas with n molecules with all identical masses, we have the energy to be and the probability density here comes out to be e to the power of minus beta p1 squared plus so on up to p3n squared by 2m, and you have to integrate over the entire range of variables divided by multiple integral dx1 to dp3n e to the power of minus beta p1 squared to p3n squared by 2m. Yeah, this is the now of because of its simple form where the energy depends only on the momenta, the volume integrals first cancel in the numerator and the denominator, so we don't have to consider the volume anymore, right? Is that clear to everyone?
So I didn't get that. Why volume cancels?
So let me write this, because this integrand here depends only on the momenta, and I also have the coordinate integrals here. So I can write it as dx and to dx3n times the integral over dp1 to dp3n times this integrand,
Yes, sir, understood. Yeah.
right?
Yes.
Divided by in the same in the denominator, you will have this dx3n times integral dp1 to dp3n e to the power of minus beta e of that. So these two will cancel out trivially, and we set about evaluating this. And for this, we noted that this was of the form. So first, the denominator is very easy to evaluate. It is nothing but, so let's first evaluate the denominator. Integral dp, it's a product of I going from 1 to 3n integrals firstly. So it looks like dpi e to the power of minus beta pi squared by 2m, right? And I told you that this integral here, this integral inside, it goes from minus infinity to infinity because each component of momentum, because the velocity can be arbitrarily large, you consider it from minus infinity to infinity. And I gave you this simple Gaussian integral formula. This integral evaluates to sigma root 2 pi. This is a very standard result. How to do this integration is something that you will learn in when you do complex analysis and all this, but this is a standard result which you can remember, which will be very useful in physics overall. So this integral inside can be evaluated by just analogy. And we did that. We got pi equal to 1 to 3n. And since each integration variable is a dummy variable, this product from I equal to 1 to 3n is essentially the same factor multiplied 3n times. Okay. And what is that factor? Mu is 0. Pi is the integration variable and sigma squared is m by beta. So it is square root of 2 pi, this factor times sigma, which is square root of m by beta. Okay, 3n times, this is nothing but 2 pi m by beta power 3n. And in the numerator, we have the following. This is the denominator. In the numerator, we now have a slightly more complex expression, which is integral dp1 so on up to dp3n. And we now have this additional factor in front, in addition to the exponent. And we also noted that this can be written as integral, multiple integral of dp1 to dp3n, p1 squared plus p3n squared by 2m times e to the power of minus beta p1 squared by 2m times e to the power of minus beta p2 squared by 2m, so on up to it's a product e to the power of minus beta p3n squared by 2m. This is a product of 3n exponentials, and you can write this is a sum, right? So you can write the whole thing as a sum from I to 1 to 3n. Okay, and there will be one p1 squared here and one p1 squared here. So there will be pi squared by 2m times e to the power of minus beta pi squared by 2m integrated over dpi. That is one integral which will be there, times an integral which has 3n minus 1 pi's in it, and it is simply dpj. Let's get pj where j not equal to I, dpj, sorry, e to the power of minus beta pj squared. Okay, this is product over all j. This is product over all j e to the power of minus beta pj squared by 2m. Okay, so this is what we have. This integral here can be written in this form. Now we know how to evaluate this. This is exactly this factor here, but with a power 3n minus 1. So what we have now is this can be written as 1 to 3n integral minus infinity to infinity dpi pi squared by 2m e to the power of minus beta pi squared by 2m times each of these terms will have a factor which is square root of 2 pi m by beta power 3n minus 1. So since it's a common factor, you can take it out. So the total expression will have this in the numerator divided by 2 pi m by beta power 3n in the denominator. So you can easily take out that factor, and what you are left with is just a factor of 2 pi m by beta in the denominator. Okay. And then we have to, and we also noted the last simplification that we did was this integral is summed over 3n times. So we can just evaluate it as 3n times integral minus infinity to infinity dp. Now I am not removing the subscript because it is just the same integral divided by square root of 2 pi m by beta. This is a vast simplification from that complex 6n dimensional integral that we started with. And all that remains now is to do this integral.
So
Yeah.
why that 3n minus 1?
Why the 3n minus 1? Because this integral here is a 3n variable integral, right?
Yeah.
And if you write this exponential as a product of 3n exponentials, and if you also multiply this into the summation, each term in the summation will be one particular variable p1 squared. Let us say the first term will be p1 squared times e to the power of minus beta p1 squared by 2m and the remaining 3n minus 1 factors.
Okay, understood.
And each of these terms, so if I write the summation as summed over I equal to 1 to 3n, there will be that particular pi times a summation with 3n minus 1, sorry, a product with 3n minus 1 terms.
Yes.
Okay, it is good to rework this calculation yourself. It is not very complicated, but it is also a little messy in terms of the details. So now we have to evaluate integral minus infinity to infinity dp p squared by 2m e to the power of minus beta p squared by 2m is what? And unfortunately, we only know this. Square root of 2 pi m by beta. Anybody has ideas? I said, look this up. How will you do this?
So we differentiate with respect to beta.
Exactly. That's the simplest way to do it, because the beta is a parameter. It's a constant. So the integration doesn't depend on beta. So if you notice, e to the power of minus beta p squared by 2m differentiated with respect to beta is nothing but p squared by 2m with a minus sign times e to the power of minus beta p squared by 2m. Right? Therefore, all you need to do is take the negative derivative of of this integrand e to the power of minus beta p squared by 2m, and that will be p squared by 2m e to the power of minus beta p squared by 2m. Now you take the integral with respect to dp. That will be integral p squared by 2m e to the power of minus beta p squared by 2m dp. So this integral is nothing but, now this beta and the integration variable are different. So you can bring this out. But we know exactly what this is. This is just square root 2 pi m by beta. Got it? So,
So the
sorry.
so the derivative is respect to beta and uh, okay, got it, sir.
Got it? The derivative with respect to beta and the integration is with respect to p. So these can be exchanged. And we got lucky because we have the function p squared. Okay. So then that is what we are going to do. So this integral, therefore, integral minus infinity to infinity dp of p squared by 2m e to the power of minus beta p squared by 2m is nothing but minus delta by delta beta of integral minus infinity to infinity e to the power of minus beta p squared 2m dp, which is minus delta by delta beta of square root of 2 pi m by beta, which is basically square root of 2 pi m times minus del by del beta of beta power minus half, which will be half square root of 2 pi m times beta power minus, right? Did we do it correctly? I think so. I think so. All right. So that's it. So now let us write down the full expression, numerator by denominator is 3n. There is a factor of 3n times this integral, which is half square root of 2 pi m times beta power minus 3 by 2 divided by square root of 2 pi m times beta power minus half. Square root of 2 pi m goes off. We get 3n by 2 and beta power minus 3 by 2 by is 1 by beta. So what we get is the average energy of an ideal gas is 3n by 2 beta. And we know from gas laws that this is nothing but 3n by 2 kT. In fact, when we derived Gibbs principle, beta was just a constant. Now we have a way to relate by applying this Gibbs principle to the ideal gas and computing the average energy. We now have a way. This comes from gas laws. Okay, by applying Gibbs principle to the kinetic theory of gases, which we know is the description of gases which gives the correct gas laws, you now have beta equal to 1 by kT. All right.
Yes.
And we see that now why is this? Now this is, I'm also saying that this average energy derivation that we did shows equipartition because of this factor of 3n here. There are 3n momenta contributing to the energy. There are 3n, the coordinates are not contributing, but there are 3n momenta which contribute to the energy, and each of those momenta is a quadratic, each of those terms of the energy is a quadratic term. And because of the quadratic term, we had a Gaussian integral. And because of the Gaussian integral, we got this nice simple expression which involved 3n by 2 beta, where this factor 3n came from basically the 3n momenta that contributed to the energy, the 3n terms of integration. Is that clear? So we have just shown how the equipartition theorem of energy is related to classical physics. How did we show that? Our expression for the energy is in terms of velocities and coordinates, or momenta and coordinates, which is an inherently classical mechanical description of energy. And using that expression, we used Gibbs principle, and Gibbs principle is a consequence of the second law of thermodynamics, which is a fundamental law, and people have not really seen a violation of second law. Sorry, there was a question. Soham, what is the question? Oh, okay. There was an earlier question saying we could have done it by integration by parts, right? You could try, but this is the simplest method. But if you had a p dp instead of p squared dp, you can then try integration by parts. That would become easier.
Sir, actually, this integration we will have to apply by parts twice.
Twice, correct. We have to apply it twice in this case.
Yeah, but this was much simpler than that.
This
Yeah,
is much
agree.
simpler, yes. And these tricks, these kind of tricks are very often applied to a whole class of such integrals. Not just this one. There are other integrals which you can evaluate in similar fashion. So in general, you can come up with an expression for x power n. Of course, all the odd powers will be zeros because Gaussian is an even function, and any odd power of x will give you an integral of 0. So that is trivial. All the even powers you can in principle come up with a formula using such a trick. Okay. It just keeps, I mean, it's very obvious, right? You can just yeah, you can also substitute p squared by t and use the gamma function. That is also perfectly fine. The idea is the following. You can differentiate any number of times with beta, and every time you differentiate, you get a factor of p squared outside. So you can in general write down the formula integral of dp p power say n 2n, let us say 2n e to the power of minus beta p squared by 2m is nothing but minus of, or minus 1 power m, sorry, minus 1 power n delta by delta beta power n of e to the power of minus beta p squared by 2m integral. Is that clear? That's a general formula. All right. And we have just shown that equipartition theorem holds here. Now, using this Gibbs principle, you can derive a lot of useful information about the ideal gas. I will leave some of these as exercises because now you know how to do these calculations. So if you ask the question, what is the probability? What is the probability that, okay, you find a gas molecule with velocity, okay, you find a gas molecule with velocity. I'm not going to do this, but I'm asking the questions and I want you to set up the integrals and do this. It is there in the notes, of course. You can look up the notes, the slides that I shared that has all this information, but you can now, it's your imagination that will limit you as to what questions you can ask. And Gibbs principle is so fundamental that you can kind of arrive at all those answers to all those questions through the Gibbs principle. What is the probability that you find a gas molecule with velocity v bar, okay, where v bar is vx, vy, vz, probability density, okay, and this answer comes out to be, you should work it out. And I can also ask a similar question. Now velocity is a vector, remember. Now what if I ask what is the probability density for a gas molecule to have a speed v? This will give you the Maxwell's distribution, Maxwell-Boltzmann distribution. For the molecular speeds, okay. So try setting up these integrals. It is a good exercise to be comfortable with Gibbs principle. The ideas are pretty much the same as what we did, just that when you talk about velocities, you have to consider the volume of integration or the integration variables to be dvx, dvy, dvz, which can easily be derived from px, py, pz as m times dvx, m times dvy, etc. So that is easy. And then once you have that probability distribution, you can ask the various questions such as what is the average speed of a gas molecule in a gas with temperature T? What is the maximum speed? So once you have the distribution, what is the maximum speed, etc., etc. All these things can be, or not the maximum speed, I mean, which most probable speed, etc., etc. You can ask all these questions and get the answers. So I leave this as an exercise, and probably I'll give a homework at sometime during the week so that all these questions are recorded and you try them. Yeah, Kenil, I have a question.
Sir, here I have a question that when we want to say specify the maximum speed of a gas molecule, so
Not
shouldn't it
maximum
be
speed.
bound?
No, no,
I am,
no, not
I am,
maximum speed. I meant most probable speed.
yes, sir, that I got it, but I am actually having the doubt regarding the maximum speed that a gas molecule can have.
You cannot say that because we are assuming that the velocity goes all the way to infinity.
And sir, that's the point that actually that's not possible. Like the gas molecules will have finite mass, right? And the
Yeah.
energy of the whole system is also finite.
Yes, yes, but we are, so that is a very, very good question. Physically, relativity prohibits you from taking a velocity all the way to infinity. We know that, right? That's what you're hinting at.
Yeah.
Yeah, that is true. But what we mean is the following. This distribution will be so sharply peaked that at the higher velocities, you don't even have to go to speeds of light. Usually the speeds of gases at room temperature, gas molecules at room temperature is of the order of a few hundred meters per second. Even if you go to a few thousand meters per second, this probability will be infinitesimally small. So those fractions don't even contribute anything. So practically, if you integrate only up to this point, you will still get the same value with almost 679's precision.
Okay, I see. Yeah. Thank you,
Yeah.
sir.
So it's all a game of probabilities. All right. Now, let us consider, instead of an ideal gas, let's now consider a system which is a collection of n independent oscillators. Okay. You can think of them as this. Let's consider a big volume which has spring mass systems, masses m and springs k, and a large number n of these. Now, the way I'm drawing it, you would wonder as to why anybody would have a system where there are so many springs and so many masses. But the picture is as follows. Consider a system that has n. N is of the order of 10 to the power of 23. Remember, it's not a small number. And consider a system that has n oscillators. Okay. N independent oscillators. So this is like an ideal gas of oscillators in some sense. These are independent oscillators. They don't talk to each other, but they are all at equilibrium with temperature T. Now we want to know how to apply the Gibbs principle to this and what is the average energy of this particular system. Now, why would we be interested in such a system? It turns out because such a system is in fact realized using a system of coupled oscillators. Coupled oscillators. Okay. So you take an Avogadro's number or roughly of the order of that number of coupled oscillators and you compute the normal modes of that system. Have you studied normal modes?
Yes, sir.
Okay, so the normal modes of such a coupled oscillator system will be independent of each other. That is the definition of normal modes. The word normal means they are orthonormal. That is, they are independent of each other. Okay, so these are the normal modes of the system. Are a set of uncoupled oscillators, independent oscillators. Okay, so now we are going to apply Gibbs principle to compute the average energy for such a system. And the average energy, what is the average energy for this system? That is the question. So how do you do this? Exactly the same way. You write the energy as a function of. So first let's write the energy as a function of the coordinates and momenta. N particles in 3 dimensions implies 3n coordinates, 3n momenta. This we are quite familiar now. So x1 to x3n, p1 to p3n. And the energy of this configuration will now be half k x1 squared plus x3n squared plus half m, or rather let's write it in terms of the momenta, p1 squared plus p3n squared by 2m. This is the energy. Therefore, if you want to do the average energy, okay, the average energy is just going to be integral over dx1 all the way to dp3n of the energy function, which is half k x1 squared plus so on to a k x3n squared, okay, plus half 1 by 2m p1 squared plus p3n squared, okay, times the exponential factor this looks more complicated, divided by integral dx1 to dp3n of e to the power of minus beta, the same expression. Now, how do we evaluate this? In fact, in exactly the same way. Okay. Now, first things to realize, the denominator is exactly the same as earlier, just that we now have factors involving both k's and x's and p's. So therefore, let us first evaluate the denominator. Okay, let's first evaluate the denominator, and what we get now is integral dx1 to dx3n. This is the spatial integral times e to the power of minus beta x1 squared plus so on up to x3n squared by 2 times k being the spring constant. I've assumed for simplicity the spring constant to be the same, times integral dp1 to dp3n e to the power of minus beta p1 so on up to p3n squared by 2m. So can somebody quickly tell me what this will give you? This and this are exactly the same, right? Just the factors of k beta and beta by m are the only two differences. Otherwise, they are exactly the same. But of course, you have to be. Is it clear to everyone? And the x1, x2, x3, so on up to that, we are going to consider the x integrals to go from minus infinity to plus infinity for each x1, x2, x3, so on up to xn, in the sense that I just described to Kenil's in answer to Kenil's question, that the final answers are going to be very sharply peaked around the average values. So you may say that since we are considering a large volume but finite volume of these oscillators, these x oscillations cannot go all the way to infinity. Well, yes, they cannot go all the way to infinity, but so cannot the velocities for the arguments that we just gave. But because these integrals are so sharply peaked around some average value, you can consider the integration limits to be practically minus infinity to infinity for all these variables. Okay, so if you consider that, you have pi equal to, sorry, this integral will be pi, the product of 1 to 3n dx e to the power of minus beta k x1 squared by 2, sorry, kx squared by 2 multiplied 3n times pi I equal to 1 to 3n integral dp e to the power of minus beta p squared by 2m multiplied 3n times. So this will be square root of 2 pi, right? This is pi 2. Yeah. So this will be square root of 2 pi by beta. There is no m there. Sorry, there is beta k. There is a k there, right?
Yes, sir.
Yeah. Times this power 3n times e to the power of, sorry, square root of 2 pi m by beta, like last time, power 3n. All right. This looks good. The denominator is solved. And to solve the numerator, let us take the numerator up separately. And we have integral. This is a multiple integral again, dx1 to dp3n of this rather half k x3n squared. This is one term times e to the power of minus beta of the full energy. This is, I'm dividing this into two terms. Okay. Plus there will be the kinetic energy term. This is the potential energy term times dx1 to dp3n p1 squared by 2m plus p3n squared by 2m times e to the power of minus beta of the full thing. Now the first integrand here, the complicated factor is in positions, and here the complicated factor is in terms of momenta, and with this we are already familiar with. So let us take up the second term first, because we already did that. So integral, so dx1 to dx3n, and this exponential also has, this exponential has the position dependent potential energy also. So let us write those terms here. It will be minus of half k x1 squared plus x3n squared times, this is all a product, so we cannot separate that, times integral dp1 to dp3n, okay, of p1 squared by 2m plus so on up to p3n squared by 2m e to the power of minus beta, all this just in terms of p3n squared by 2m. So this is exactly the integral that we now know how to solve. What will this be? This will be 3n, right? What will this be? It will be 3n. Can somebody tell me? Dou by dou
Sir.
beta of square root of 2 pi m by beta sorry, let's not correct. Yeah, square root of 2 pi m by beta times square root of 2 pi m by beta power 3n minus 1. All right, is that okay? There will be a summation of 3n terms, so that gives the factor 3n, and each of those terms will have a 3n minus 1 factor of just the simple Gaussian integral, and there will be one term which will be integral of p squared e power minus beta p squared by 2m, which will give me this factor. Is that calculation transparent to everybody the way I did it, or do you want me to repeat it? Since we already spent time in the previous problem, I'm applying those results here directly. That's all I'm doing. Any questions? This is the time to ask. All right. So I'm assuming you are okay with this. Then this is just this factor. So the total factor will be this times that. Okay. So let us now write it as, and this we know exactly how to solve. This space integral is what we solved in the denominator, which is just this. So it will be square root of 2 pi by k beta whole power 3n times 3n times minus delta by delta beta square root of 2 pi m by beta times square root of 2 pi m by beta power 3n minus 1. That is the momentum. So this in this numerator, this is the second term. This is the second term in the numerator. All right. Now what is the first term in the numerator? Let us take the first term in the numerator. See, this is the way to solve these integrals. You break them up into forms that you are already familiar with and solve those forms and then modularly put them all together. And you will see very nice cancellations happen in the numerator and denominator, and ultimately you will get an answer which is strikingly insightful. Okay, so that is the beauty of Gaussian integrals. So let's do the first term. The first term is nothing but you have integral dx1 to dx3n of half kx1 squared plus k x2 squared so on kx3n squared times e to the power of minus time. There is an integral. Oh, there is an integral of e to the power of minus beta k x1 squared by 2 plus so on. Okay, times the p integral e to the power of minus beta p1 squared by 2m plus so on up to p3n squared by 2m. Now this by symmetry, this product term here is nothing but square root of 2 pi m by beta power 3n. So you can write the whole thing as square root of 2 pi m by beta power 3n times this space integral now. And how do we do that? That
Sir, that
by
will be completely analogous, right?
exactly completely analogous. So let us now write that instead of, it will be 3n. 3n factor comes from, by just looking at this term, I can write down it's going to be 3n times minus delta by delta beta of 1 by square root of 2 pi by k beta times square root of 2 pi by k beta power 3n minus 1. For an extremely complicated looking integral, we have solved it in under 6 minutes. So now we put together the full result together. First term plus second term divided by denominator is the answer. So let us do this. So first write down the denominator. It will be square root of 2 pi by k beta power 3n square root of 2 pi by m by beta power 3n. This is the denominator. And the numerator has the first term, which is square root of 2 pi by 2 pi m by beta power 3n times 3n. 3n is now common to both. And then you have minus delta by delta beta square root of 2 pi by k beta times square root of 2 pi by k beta power 3n minus 1 plus, I'm going to write this as a second term, square root of 2 pi by k beta power 3n square root of 2 pi m by beta power 3n. The roles of 3n will be the same, minus delta by beta. This time it will be 2 pi m by beta, and there will be a factor of square root of 2 pi by k beta power 3n and square root of 2 pi m by beta power 3n minus 1. Do all the calculations, all the cancellations, and what you now get ultimately will be the following. So here this factor goes off, so you will be left with 1 square root of 2 pi by k beta, and here square root of 2 pi by k beta, sorry, this factor completely goes off, and similarly this factor completely goes off here, and this factor leaves 1 2 pi m by beta. And the beauty of this is this 2 pi m and this 2 pi m get cancelled, and this 2 pi by k and 2 pi by k get cancelled. So the mass of the particles and the spring constants of the springs will completely go out of the picture, and we get a result which is 3n by 2 beta plus 3n by 2 beta, which is 3n by beta. Verify this. I think the calculation is fairly trivial, right? Anybody did not understand how I went from this step to this step? I just did the differentiation in my head, of course, but the differentiation only depends on beta, and the square root of 2 pi m factor there and the square root of 2 pi m in the denominator, they cancel out, and we already saw that it gives you a factor of 1 by beta, but there are two terms now. So you now get 3n by 2 beta plus 3n by 2 beta, which is 3n by beta, which is, because we know that beta is kt, is nothing kbt, where kb is Boltzmann's constant, not the spring constant. You get 3n times kbt. And how do we interpret this? The energy term has 3n quadratic x terms and 3n quadratic p terms, and each quadratic term in the energy, gave a factor of 1 by 2 beta which is equipartition. Okay, so what we showed was that a collection of n oscillators, unlike an ideal gas, because the energy of the oscillator also depends on positions through the potential energy, you now have to take into account that contribution also, and due to the absolute what to say beauty of Gaussian integrals, you get the simple result that it doesn't matter how complicated the shape of that quadratic term is, as long as it's a quadratic term, I will get 1 by 2 beta per quadratic term in the energy. So this is the equipartition of energy, and what this means is if you have a collection of oscillators all at equilibrium temperature T, you will have an equipartition of energy which is a function of the temperature. Okay, now we will stop here for today. We have looked at how to use Gibbs principle for various calculations. On Wednesday, we will take up the black body radiation and see how this equipartition of energy results in what you familiarly know as the ultraviolet catastrophe. Okay, so the scheme of things will be as follows. We will first establish that electromagnetic radiation is a collection of harmonic oscillators. And once we establish that connection, equipartition theorem immediately follows if you apply classical analysis, and that immediately leads to Rayleigh-Jean's law, which blows up at the high frequencies. Therefore, we will then use that to motivate why we need Planck's distribution and what is different from what is different between the classical equipartition theorem and Planck's distribution. That will be our segue into modern physics, starting next lecture. Any questions?
Excuse me, sir.
Yeah.
So can we relate this energy we got with degree of freedom as well, like the partition?
Oh, absolutely right. I mean, these 3n are the degrees of freedom.
So like we considered the potential energy here, so like that resulted into like 2 degrees of freedom. Like we expected that not to in the case for the last, like we got like 3n kBt by 2 last time when we didn't consider any potential for that.
Correct.
Here we considered the potential also, so like it added the degree of freedom or something.
Yeah.
Okay, sir.
So yeah, velocities and potential and coordinates contribute to energy. Ideal gas was a simple case where only velocities contributed. Here we also, in an oscillator, you also have the potential contributing, and each contributing term of each contributing quadratic term of the energy will result in an average energy of 1 by 2 beta or kb by 2, kbt by 2. So this half kbt per degree of freedom is the statement of the equipartition theorem. And these two classes of problems, free particles and oscillators, are pretty much universal because you can treat to a very great approximation many systems using one or the other of these pictures. If you have a very complicated mess of coupled oscillators, you can go into normal modes, assuming you can compute the normal modes. As long as these oscillators are linear, you will have terms. The normal modes will be harmonic oscillators, which means the terms in the potential energy and kinetic energy will be at most quadratic. If you have nonlinear oscillators, then of course this is a very, very different deal. So we have to treat that very differently, and it's not so easy. But nonlinearity is always a feature that occurs when the amplitude of oscillation grows beyond a certain value. Even nonlinear oscillators behave pretty much linearly for small oscillations. And I showed in the very beginning that oscillators play a very big role in physics because small oscillations can happen for any physical system, right? If you have any physical system with a potential u of x, if this potential has a minimum, it doesn't even have to be a global minimum. Around every local minimum, this, let us say the local minimum is x naught, you can expand this Taylor series. Sorry. Plus so on. And if it is very close to x naught, these higher terms can be neglected. And by the definition of a local minimum, the derivative with respect to x at that x naught will be 0. So the potential essentially to lowest order becomes a constant plus a small parabolic term. And this term, because of the criterion that this is a minimum, because this is a minimum, del squared u by del x squared is a positive quantity, which means every potential with a local minimum close to that local minimum will behave like a harmonic oscillator. This is the special significance of harmonic oscillators, which comes from this property. Whenever you have a minimum, if you take the system which is at equilibrium at that minimum, perturb it slightly, the system will experience a restoring force which tries to get it back to that equilibrium position, and that force will be harmonic, will be like Hooke's law, and you will have a simple harmonic oscillation. So even systems with nonlinearity can be linearized in this fashion for small amplitudes, and you can treat the oscillations there. Any questions? If not, we'll conclude here, and we will see on Wednesday where we will discuss the black body radiation, and after that it will be we have finished thermal physics portions. There is still time for the second homework that I gave you, and I will give you a third homework this week, which deals primarily with Gibbs principle and calculating various things like Maxwell's probability distributions and other things. This will not be a graded homework because the notes that I gave you will have all these results anyway. But I want you to give a homework so that you try these derivations yourself and get comfortable with them. And that will give you a working understanding of Gibbs principle. And there won't be any deadline for this homework, so you can take your time. The sole purpose is for you to solve these, set up these integrals yourself and try to compute various quantities. All right. So we'll meet on Wednesday.